Hello, everybody, and welcome to the Thermochemistry Unit 15 review session. Your test, let's talk a little bit about that. The format of that test is going to be 6 multiple choice questions, and then you will have 8 free response questions. All right. As far as information that we are giving you are constants. The constants that we're going to be giving you are right here on the back of this periodic table. You can see them right there. All right. You can pause if you need to. Giving you the specific heats for the 3 states of water and both the enthalpy of fusion and enthalpy of vaporization. So those are the constants. You will not be given any equations. All of those you need to know yourself. Okay. So let's go over. I have several review session problems to go over with you today. Let's start going ahead and start with number 1. What would be the final temperature of a mixture consisting of 302 grams of water at 95 degrees and 411 grams of water at 5 degrees? So you have hot water and you are mixing it with cold water, and I'm asking you for the final temperature. Well, the final temperature is going to be something in between the 95 and the 5. All right, keep that in mind as we go on ahead solving this. So this is an example of a heat lost is equal to heat gained. All right, and when we're talking simply about changing temperature, that is going to be a specific heat problem. So just as a reminder, our specific heat question, which is our specific heat equation, which is MCAT, is Q, which is heat, another word for energy, is equal to the mass times the specific heat times the change in temp. All right, that's why we call it MCAT. Okay, so in this case, we're going to set 2 MCAT equations equal to each other. First, dealing with what's losing the heat, and what's losing the heat is the water that's at 95. So you have 302 grams, that's your mass. So 302 grams of water. Your specific heat of liquid water, 4.18. All right, and then your delta T, and this is where we need to take a moment. We're looking for that final temperature. All right, the way that I like to do these problems is I always make that delta T a positive number. Okay, so I say to myself, will that final temperature, my X, will it be higher or lower than 95? Well, this water is going to be cooling down. It's losing heat. So that X is going to be less than 95. So 95 minus X is going to be how we set that up for the heat lost. Okay. Now, who is gaining the heat? Well, this 411 grams of water. Liquid water still, so my specific heat. All right, now for the delta T of this one, it started at 5 and it's going to end at our final temperature, which we're not sure about. So which one is going to be higher? Well, it's going to gain heat. It's going to raise in temperature. So that X is higher, so that is X minus 5. And that both delta T's are in change in temp. Are in degrees Celsius. All right, so now what we can do to make our math just a little bit faster is you can divide 4.18 out from each. All right, and then you're going to go on ahead and do the algebra to solve for this. I will just show a really quick screenshot of the algebra to save a little time on this video, but you can just take a look right there with me working it out. All right, you can pause if you need to. And when you finally get your final answer, X is going to end up being equal to, I'm double checking, looking at my handwriting. So 307 is 43.1. Now, when you get a final answer like this, you do want to make sure that it makes sense. So say to yourself, okay, well, 43.1 degrees, is that between 95 and 5? It absolutely is. So that's always a good check that you did your work correctly. Please make sure, as if all of our work, that you're showing all of your setup, just in case your algebra does not work out. All right, it's just simple distribution, right? And then you're adding your X's. So you have X on one side, adding just your numbers. So you have those on one side. All right, so please make sure you have that algebra down, and this should be your final answer. Okay, let's take a look at number 2. All right, number 2, if the specific heat capacity of an unknown metal is 0.94, how much energy would it take to raise 95 grams of this from 20 to 150? So this is just, again, a very simple MCAT situation. Okay, we're looking for how much energy. Q is just heat, it's a form of energy. So you are dealing with 95 grams. The specific heat of this metal is 0.94. And the delta T is, sorry, mine kind of went off the paper here. I went from 20 to 150. You want to make that delta T a positive number. So 150 minus 20. All right. You're just going to end up multiplying that all together. And you get a final answer of about 11,600 joules. You could certainly write 11.6 kilojoules if you'd like to. There's no reason to convert it, but if you did, that would be perfectly acceptable. Okay, so nice, very straightforward problem there. All right, next up, number 3. How much energy is needed to turn 19 grams of water at 36 degrees to steam at 115? All right, so in this problem, you're dealing with water at 36 degrees. Well, at 36 degrees, we know that we have liquid water. And I want to know how much energy it takes to get it to be steam at 115. I think it's a really good idea to set up the graph to give you an idea of how many steps you're going to do. So I'm starting at 36. It doesn't really matter where you start the graph. So I am going, or where you actually draw the graph from. Remember, it's temperature here, energy here. All right, I'm at 36. I am going to be raising this up until it gets to its boiling point, which for water, of course, we know is 100. So I'm going to raise that up till I get to 100. At 100, it is going to vaporize. Okay, so when I vaporize, remember temperature doesn't change, but energy still does. So we're going to get that plateau. I'm not done at just the end of 100. I go up to 115. So that is how my graph should look. As far as how many steps this problem is, my first problem is going to be a specific heat problem where I change the temperature. The second is going to be a change of state. And the third is going to be a change in temperature again. So let's take a look, see what that looks like. So step 1, you're changing the temp. That's just an MCAT problem. So your Q is going to be 19 grams. At this temperature, we are liquid water, so 4.18. All right, and then for my delta T, I'm going from 36 up to the boiling point, so up to 100, so 100 minus 36 degrees Celsius, okay? And I'll find my number for that, and that'll be great, okay? Then number 2, part 2, I am vaporizing. So in this case, when you're changing state, remember there is no change in temperature when you change state. So the equation is just simply the mass, which doesn't change, that's 19 grams. In this case, you're vaporizing, so the enthalpy of vaporization, which again, you'll have that constant there. So the enthalpy of vaporization for water is 2260, right there. So 19 times 2260, and that's simply in joules per gram. Remember, no temperature involved there. Step 3, we're increasing the temp again. So we're going back to our MCAT, 19 grams. But be careful, now you're at steam. You're not at liquid water anymore. Now you're at steam. So you're going to go back over and you're going to take a look. The CP of steam is 1.7. So 1.7, that's joules per gram times degrees Celsius. And then your delta T for this is 115 minus 100. Because we were at 100, we went up to 115. Okay. Once you have all of this work, it's then time to grab your calculator and you can do the math for it. Step 1 up here should have given you 5,083 joules. Step 2 should have given you 42,940 joules. And step 3 gives you 485 joules. So you're going to add those 3 numbers up to give you a final answer of about 48,500 joules. All right, certainly you could write your answer as 48.5 kilojoules. That would be fine as well. All right, so again, just to kind of restate, I find it really helpful to do one of these graphs to identify how many different steps I'm going to have in one of these change of state problems. Okay, let's take a look at number 4. Number 4. An unknown metal with a mass of 20 grams is heated to 106 degrees and dropped into 50 grams of water at 15. If the final temperature of the mixture is 26, what is the specific heat capacity of the metal? This is just like the lab that we did. And again, this is going to be a heat lost is equal to heat gained situation. So you have 20 grams, all right, of your metal. So you have 20 grams. We don't know the specific heat of that metal. That's what we're looking for. As far as the delta T, that metal started at 106. The final temperature of the mixture is 26. So 106 minus 26. That's going to lose heat. Where did it lose it to? It lost it to the water. How much water? You have 50 grams. We know specific heat of liquid water is 4.18 joules per grams times degrees Celsius. As far as the water, it started at 15 and it ended at 26. All right, so your change in temp is 26 minus 15 degrees Celsius. If you were thinking, how did I know to use 4.18? Well, at the temperatures where water is, between 15 and 26 degrees, it is liquid. So that's how we knew which specific heat to use for water. All right, so you have your whole setup here. Once you go on ahead and solve for that specific heat, you find that your specific heat should be about 1.44 joules over grams times degree Celsius. Okay. All right, excellent. Okay, moving on. The next part of our unit dealt with energy in relationship to a specific chemical reaction, and we call that the enthalpy of reaction. Enthalpy is just another word we use for energy. It is given to you along with a balanced equation. Now this one dealing with, X's and Y. I made all of these numbers up, but here's your balanced equation and here's the delta H that goes with it. A couple things that you can already tell from this, what I've given you. This is an exothermic reaction. It has a negative delta H, which means that this reaction gives off energy. All right, so that's certainly something I could ask a multiple choice question about, that type of thing. How much heat is associated with the reaction of 55 grams of Y with excess X? The molecular weight of Y is 115 grams. So I'm asking for heat. That is another word again for energy. Only energy unit we have going on here is kilojoules. So I'm going to be looking for kilojoules in my problem. I'm going to start with the information I was given. So I have 55 grams of Y. Anytime you start with one thing and you end with another, as we have here, we are going to factor label. We're going to get to the mole because it's the mole that's going to allow us to go from one thing to another using the balanced equation. So I gave you the molecular weight of Y, so 1 mole of Y has a molar mass of 115 grams. Now I'm going to come up to my balanced equation and use the coefficient. I have a coefficient of 2 there for Y. So 2 moles of Y for every 196.1 kilojoules of energy. So 196.1 kilojoules. Okay. Again, the delta H is connected to this balanced equation. So I'm going to go on ahead and I put all of my values in, and you just simply get 47.0 kilojoules is your final answer. That's how much heat is associated with this reaction. Okay. And again, I could continue and ask, is that heat given off or taken in? And you know it's given off because it is a negative delta H. It is exothermic. Okay, let's use the same balanced equation and kind of just go in the other direction. How many grams of XY are formed when 8,500 kilojoules of energy is used? Okay, well, now we're looking for grams of XY. We're starting with the only number I gave you to start with the energy, 8,500 kilojoules. Okay, well, using the balanced equation, I know I have this many kilojoules for that many moles of XY. So let's go on ahead and put that in. I'll try and keep both things in camera. All right, so 196.1 kilojoules for every 3 moles of XY produced. Okay, so from the balanced equation. My next step is I'm going to convert from moles to grams. All right, and I've already told you up here for every 1 mole of XY, my molar mass or molecular weight is 215 grams. Always double checking your kilojoules divide out, your moles divide out, you're left with grams. That's what you're looking for, grams of XY. And you should get an answer of about 28,000 grams, or you could write 28 kilograms. Either one is great, perfectly acceptable. Okay. All right, we're gonna go over one more problem together, and that is dealing with Hess's law. Okay, so this is gonna be number 6. And remember with Hess's law is when we can't directly find the delta H for the reaction we're interested in, we can use other reactions, add them up, and get the delta H for your desired reaction. So that is what we are going to do. All right, and bear with me with these. They can get a little sloppy as you do them, so really try and kind of stay as neat with everything as you possibly can. Okay, so here's my desired reaction. And this is going to be important that we keep this in mind the whole time. And we are looking for the delta H of this reaction. That is our goal. Okay. We are going to use these. I call them smaller equations. They're not really smaller, but I just mean they're the ones that are going to build up to what we are looking for. And there's steps that you need to follow. Okay. And it's really important. I think it's important that you go in a particular order. So the first step that we're going to go through is we're going to say, are the reactants and the products on the correct side? And by side, I mean side of this arrow. All right, our reactants where reactants are supposed to be and our products where products are supposed to be. And I just simply kind of go through, all right, reading from left to right. B2H6, all right, it's a reactant in my desired. It's also a reactant down below, so I don't have to do anything at this point for that one. Okay, so now I'm going to go over to Cl2, all right. So Cl2 is a reactant, okay, in my equation. It is also a reactant down here in my products, so that's good to go. Okay. BCl3 is a product, so it needs to be a product down here. So BCl3, well, if I look at my smaller equations, BCl3 is a reactant, so I'm going to have to flip it, and that's fine. What I do when I'm going to flip it is I go ahead and rewrite this equation, flipped to the reverse. So H3BO3, okay, plus 3HCl is going to give me BCl3 plus 3H2O. Okay. I am then going to change the sign on the delta H, because if this forward reaction is exothermic, then the reverse, which is what we just wrote up there, is going to be endothermic. I now cross this out. All right, I cross this out because I'm not dealing with that equation anymore. Okay. All right, so now I have BCl3 is on the correct side. All right, we already established B2H6, Cl2, BCl3 is on the correct side. Now my hydrochloric acid. Well, hydrochloric acid I have on the left and the right. If that occurs, just kind of leave it, most likely, or it should work itself out. Once I have things on the correct side, that's step one. Now I'm going to make sure I have the right amounts of things. And by amounts, I mean the coefficients. All right, so for B2H6, I have a coefficient of 1 in my desired equation, and I have a coefficient of 1 down here. Good sign, I'm good to go. Okay. For my Cl2, all right, I have 6 Cl2 up in my desired equation, and I only have a half of a Cl2. Now, the halves I know seem weird, but with Hess's law problems, halves do show up. So I need 6, I only have a half, so I'm going to go ahead and multiply this to get this number to be a 6. And we know what we have to multiply that by is 12. All right, because 12 times 0.5 is 6, and I need it to be 6. So that's fine, but if I'm going to multiply this by 12, I also have to multiply my delta H by 12 as well. So keep that in mind. So I'm going to go ahead. So 12 times 0.5, so that's 6H2 plus 6Cl2 is going to give me 12 HCl for now. Don't forget now, cross this off so you're not looking at it anymore. Okay. All right, so far my B2H6 looks good. My Cl2 looks good. Now I need to look at my BCl3, which is here. Okay. Well, I only have 1 down below, but I need 2. So I'm going to have to multiply this by 2. Remember, whatever you do, you've already changed the sign on this, and now you also have to multiply that by 2. Okay. I'm going to go ahead and do this. So this is going to give me 2H3BO3, okay, plus 2 times 3, 6 HCl, is going to give me 2 BCl3 plus 6 waters. Okay, great. So again, double checking, B2H6. I've got it here, and I'm going to go in ahead and actually box my desired ones and check them off. Good, B2H6, 6Cl2, 6Cl2, 2 BCl3s. All right, my 2 BCl3s right there, and I check. And my 6 HCl's. Well, oh, I've got something going on, but that's okay. Let's go on ahead and look at our next step, which is to cross off anything that occurs on both sides. All right, so, oh, I almost forgot. I need to cross this whole thing out so I don't look at it again. So I am now looking at 1, 2, 3 equations. Do I have anything that's exactly the same on both sides? Well, 2H3BO, 2H3BO. So those get crossed off. I have 6 HCl's and I have 12 HCl's. So the 6 goes away, that 12 turns into a 6, and right there, there's that 6 HCl. So good and check, okay? Also make sure everything else gets crossed off. I have 6 waters here, I have 6 waters here. Perfect. Okay, and then finally, and I know it can start to get very sloppy, 6 H2s here and 6 H2s there. That's a really good sign that everything's going well. You're then going to add all of these up, and when you add all of these up, remembering that you had to change the sign on that one, you're going to leave this middle one actually completely alone, and that bottom gets multiplied by 12. You should get a final answer of negative 1367 kilojoules. All right, so make sure, practice putting this in your calculator and that you're doing everything correctly with those negative signs, okay? All right, everybody, good luck on your test and have a great day.